Your DFS from that vertex is going to include everything that's reachable from the vertex that hasn't been visited yet. Okay, so if it's reachable and it's already been visited, great. Then it's been dealt with, it has a finish time, and it's in the list, so it's further to the left than the place where you started. Otherwise, it will, in your DFS, when you visit a vertex, you will explore everything that can be reached, and then you will finish that stuff before you finish this vertex. So when you get back to the vertex for the last time and you finish it, and you put it in the list, everything that can be reached from there is already in the list, right? Because if it weren't already in the list, then the DFS has missed it and you've implemented your DFS incorrectly. So that's topological sort. So if you want, the proof is in CLRS. There's this long lemma this, proof that this works. But the main idea is, if there's a cycle, it will detect it. If there's no cycle, when you add something to the list, everything that's reachable from it has to already be in the list. Okay? That's okay. Because now we're on to our second third of the class. And so we're going to do, now this time I'm actually going to, am I going to copy the graph? Yes. I'm actually going to copy the graph this time. So if we had an in-person class, I might be tempted to actually wear a tie, but probably not. I think I have a tie. I think I may even have two ties. I haven't seen them for a while. They're probably in, I think they're probably in the top drawer. Okay, so now we're going to do another application of topological sort, which is strongly connected components. So strongly connected in a directed graph, okay, so if you have a vertex and a vertex and a vertex and a vertex and a vertex, and you can go, and this is U, and this is V, okay? So you can go from U to V, and you can go from V to U. So they're in the same strongly connected component. A strongly connected component of the graph is a subset of the vertices, a maximal subset of the vertices, such that for any vertices U and V in that subset, you can get from U to V and you can get from V to U. Okay? So it's maximal, it means this isn't going to work if you add any more vertices. Is it clear what a strongly connected component is? Okay, so within a strongly connected component, you can get from any point to any other point, and you can't add no, it's maximal in the sense that if you add anything else, the property breaks. So if it were minimal, it would mean it's as small as it can be. But this is, okay. I've used up 5 minutes. Okay, so what's the algorithm is a little bit weird. So, yeah, we don't need this. Just gonna, I should get, maybe there's a lighter version of this book. I should get this on my e-reader or something. That would be lighter. Okay. Okay. This looks about right. A, B, C, D. E, F, G, H. Okay. Okay. So how do you find the connected components? Well, again, when you start, you don't know anything about the graph, so you're going to pick some vertex and explore. So, which vertex do we want to choose? So we're going to do a DFS. Do people want to start at A again? Do they start at A? They don't start at A in the book. But we like starting at A? Okay. So opening time is 1. And then where can we go? We can go to B. Opening time is 1. Start time, opening time, whatever. And we can go to, well, we can either go to F or C. It doesn't matter. Let's go to F. Opening time is 3. We can only go, oh no, we can also go to E. Okay, but we will do that later. We can go to G, 4. From G, we can go back to F, but that doesn't matter. We've been there. We can go to H, so this is 5. And now we can't go anywhere from H except to H itself, so it's 6. We go back to G, it's 7. We go back to F, it's 8. And now where can we go? Well, we go back to B, but we don't close B because it's, we're not done. We go here, say, and it's 9. We can't go anywhere except F, and we've been there, so this is 10. We go back. This is 11. This is 12. No, sorry, this is 11. And, oh, if you start at A, you actually do everything in one DFS. Maybe that's why they don't start at A. Okay, 12, 13, 14, 15, 16. Okay, so that's our DFS. And what does it tell us? Not much. It tells us that the underlying underlying graph is, it tells us that you can get from A to everywhere. That's something. But we don't know if you can get from everywhere to A. So what are we going to do? We're going to compute what's called the transpose of the graph. Why is it called the transpose? So this just means you take every edge and reverse it. Why is it called the transpose of the graph? Because if you write the adjacency matrix of the graph, then it's taking, then the transpose of the graph, the adjacency matrix of the transpose of the graph is the transpose of the adjacency matrix of the graph, right? Because if before you had an arrow from A to B, so from in the first row and the second column you had a 1, then when you take the transpose, that 1 is going to move into the second row and the first column. Okay, so it says that then it's going to say that there is an arrow from B to A. So that's why it's called the transpose of the graph. Okay, so I have to do this again. Okay, this goes here, this goes here. These actually just get reversed. This goes down, this goes up, this goes like this. This goes up, this self-loop reverses, whatever. Okay, is that everything is reversed? Okay, so now we're going to do more DF. The self-loop stays the self-loop. Yeah, I turned it around, but that doesn't matter. So now we're going to do more DFSs, but I just have to remember the decreasing. Yeah. So we're going to do the DFSs in order of decreasing finish time. Okay. So you're going to start, this means that you're going to pick the vertex with the largest finish time, and you're going to start a DFS there. And then once you're in that DFS, you're going to ignore the finish times. Okay. So what's the largest finish time? It's A. And we say, okay, 1, and we can't go anywhere, so it's 1. Okay? So that tells us that this is a strongly connected component. No, wait. No, sorry, because we can't get away. Sorry, that doesn't, yeah. I didn't notice that edge. We do not do the closing time. Okay. We go 1, and we can get out of A. We go to E. So that's 2. And where can we go? We can go to B, so that's 3. And now from B, we can't go anywhere except A, and we've been there. So this is closing time 4, 5, 6. So this DFS explored these 3 vertices. That is a strongly connected component. Okay, now that we actually do this correctly. Okay, so that was 16, 15, 10. What's next? Well, it's 14. So we start here and we say, okay, that was 3, 4, 5, 6. So the start time here is 7. And where can we go from here? Well, the only place we can go is D, I think. So that's 8. And then we are stuck because we can only go back. So we finish with D, 9. We come back. Now from C we could have gone to B, but we can't because we visited there. So this is 10. And we can't do anything else, so this is a strongly connected component. And where else do we want to go? This is 14, 13, 16, 15, 14, 13. Where is 12, 11, 10, 8. Right, okay. Next one is F. So we've done, so this is 11. And where can we go? We can go to G. So this is 12. From G, we can go to C, but we can't. We've been there before. We can't get to H. So this is 13. This is 14. And that DFS is done. So that's a strongly connected component. And then H, 15, 16 is its only strongly connected component. And now we look at the book, and yes, that looks about right. Okay, so this is the algorithm. Do a DFS, and then transpose a graph, so just reverse all of the edges, and then do DFSs. And always, when deciding where to start your DFSs on the transpose, take the vertex that hasn't been visited, that has the largest finish time in the first DFS. Why does this work? Okay, so there are pages of proof of correctness in the book, but we don't really have that much time. I should put this on Do Not Disturb. We have 10 minutes. So I'm not going to go through all of that detail. Instead, I'm going to argue that if you think about the connected components, So imagine imagine you knew the connected components somehow. And you drew another graph where each connected component was a single vertex, right? So you have a vertex, and this vertex this represents, say, A, B, and C. Okay? So A goes to B, B goes to C, C goes to A. But we don't care what's in there. Okay, this is just going to be an argument about how this works. Okay, now in the original graph, okay, and you have C and D. In the original graph, you can go from you can go from B to C. So this means you can go from this vertex to this vertex. You can get from this strongly connected component to this strongly connected component in the original graph. Forget the transpose for the moment. Why is it important to detect strongly connected components? So you don't get stuck when you go off wandering. I hadn't actually been anticipating this question. Because it's useful to know that like A can send to B and B can send to A, right? Why is it important? In networks, it's sort of important, communication networks. What do I use it for? I have used it. I'll have to get back to you on that. But for example, if you go out for a drive or something like that, and you have a map of the city and it shows one-way streets, or if you're designing your city with one-way streets, you want to be sure that it's all one strongly connected component. You don't want there to be places where somebody can drive down a street and never get back. I'm not sure, there probably are places like that. I mean, maybe you can get back eventually, but maybe not. Okay. But you can see that would be bad. Okay, I will think in the lecture notes. I will try to think of I'll try to find applications for this. But graph theorists love this stuff. So you get certain properties like tokens. You don't want to get stuck if you're token passing. So you don't want the token to get stuck somewhere. Or maybe you do. If you're analyzing certain finishing times, then you don't. Okay, but for now, proof of correctness in 6 minutes. Okay, so you can go from here to here. Now, where else can you? Okay, so you have F and G. You can get to F and G, right? So you have F and G. You can get from A, B, and C to F and G. You can get from C and D to F and G, okay? But notice that you can't get from F and G back, right? Because you can't, if you go from A, B, and C, if you could get to F and G and then somehow you could get back to A, B, and C, then it would all be one strongly connected component. Yes, there should be. I mean, okay. Can check if so. Something like, I don't really do networks. Not real networks, abstract networks. Okay, so what else is there? Then there's just H, And you can get from F and G to H, and you can get from C and D to H, but you can't get from H to any of these, otherwise it would be in the same strongly connected component. So what is this graph? This graph is a DAG, a directed acyclic graph. It's not a tree. It would be nice if it were a tree. But in general, it's a DAG. Now, when we're doing the DFSs here, we're starting with a vertex, and we're doing it in decreasing order of finish time, right? So if you think about it, is it possible for somebody in C and D to have a smaller finish time than H? No, it's not. Because if in the DFS, no, we had one DFS here, you could have more than one, and you do, I think, in the example in the book. If you started your DFS at C and D, you'd actually get all of the stuff reachable from C and D. So you'd get all of these. So now, if you consider, so if the thing that you can reach the most from, this is going to have the largest finish time. Right? Somebody in here is going to have the largest finish time, because if you start in here, your DFS is going to take in everybody else, everything that's reachable from this component. So forget these little graphs in here for the moment. Do I actually need these? Forget these for the moment. Those don't matter. So you're going to be starting with somebody that can reach a lot of stuff. You can't, when you're doing your DFSs in the transpose, you can't be starting at one of these where you could go from here to here, and you start your DFS in the transpose here when this hasn't already been done. This stuff in here is going to have a larger finish time than stuff in here. Why does that matter? Because when you take the transpose, you're essentially reversing all of the edges here. Okay? So now this is going to look like, because if you could get from F and G to H, when you flip the edges around, you can get from H to F and G. Okay? So before, you could reach everybody here, so from this vertex. So now somebody in here is going to have the largest finish time. So we're going to start with somebody in here. Now everybody in here could reach everybody else in here, and that property remains true when you reverse all the edges. Okay, you don't change the connectivity within a strongly connected component when you reverse the edges, when you take the transpose. So now you're going to start in this vertex, you're going to explore it, and you're going to see everything in here, and you're going to be stuck. You can't go anywhere from here because you've reversed the edges. You could leave before, but now you can't. So now it's sort of, okay. We're running out of time for Dijkstra's.